In this section, we're going to discuss buffer solutions. Quite simply, buffer solutions contain a significant amount of both a weak thing and its conjugate. So either a weak acid and its conjugate base, or a weak base and its conjugate acid. These solutions are really important in both biological and chemical processes because they're able to maintain a solution at a designated pH range. The way they do this is because these solutions contain both an acid and a conjugate base, they're able to neutralize any added acid or base. So if I add any acid, the conjugate base is able to neutralize that. If I add any base, the acid is able to neutralize that. And because it neutralizes that added acid or base, these solutions resist pH change. So the pH will still change a little bit when you add acid or base, but a very small amount compared to just a solution of water, for instance. The easiest way to make a buffer is you take a weak acid or a weak base, and then you add a salt that contains the conjugate base or conjugate acid. So for instance, let's say I wanted to create a buffer that involved acetic acid. Well, if we write the equation for acetic acid reacting with water, we can see that, okay, acetic acid is an acid, it will donate its hydrogen, and it will create the acetate ion and that H3O+. So if we wanted to make a buffer, we would need to add this acetate ion to the acetic acid. Well, you can't actually isolate ions for very long. Ions are very reactive, and it's really hard to just get a pure sample of those. So an easier thing to do is attach this conjugate base, this acetate ion, to a neutral ion to create a salt. So for instance, here we have sodium acetate. By putting in sodium acetate, it's going to dissociate. The sodium ions are going to float away and do basically nothing. So we don't worry about the sodium at all because it's a neutral ion, and so it's just in solution, but it's not going to affect the pH at all. And really, that's all we care about. So by putting in the weak acid and this salt that has the conjugate base, we're able to create a buffer solution. So this solution now has significant amounts of both the weak thing and its conjugate. Now, a lot of what we're interested in is the pH of these solutions. Again, buffers are used to keep the pH of a solution in a designated range, which means we need to know what the pH of the buffer itself is. Now we see, all right, I have a weak acid equation here, and the only difference from normal is that I start out with some of this conjugate base. So the easiest thing to do is do what we know and solve an ice table problem. So for instance, let's say I want to determine the pH of a solution that's 0.15 molar in acetic acid and 0.1 molar in sodium acetate. So again, I can write out the equation for the acetic acid reacting with water, which we have right here. It generates that conjugate base and H3O+. I could make an ice table based on that. And the only difference from just a straight weak acid problem is that not only do we start out with some of this acetic acid, which we plug in, but we also start out with some of the conjugate base, the acetate ion. And so we have to plug that guy in as well. But after that, things are really simple. We still start out with 0 of the H3O+. Our changes are still basically negative X and positive X. And we use those to get to the equilibrium row, which we plug into the Ka expression. So if we look up the Ka of acetic acid, it's 1.8 times 10 to the negative 5. So we plug in our Ka, and then we plug in everything from the equilibrium row. Once again, we can use X is small, since K is small, X must be small, and we can do that every time we add or subtract. The whole premise of X is small is adding or subtracting a small number makes very little difference. And we get to this expression here, and we simplify. We solve for X. We see that X is equal to H3O+, and therefore if we negative log that, we're going to get the pH. And we always do the 5% check to make sure our X small approximation was valid. So this is just an ice table problem. We've done this before, and we could do it for basically all of our buffers, and life would be really simple that way. However, we can also take a little shortcut if we make some important observations. So we made the X is small approximation here, and when we do that, we see that basically what happened is when we plug these numbers into the Ka expression, we assumed that the initial concentration, 0.150 of the of the acetic acid didn't change, and we saw that the initial concentration of the acetate ion didn't change, again because X is small. So it kind of makes us think, what's the point of doing this ice table? These numbers are going to basically stay the same, and this last number is always going to be X. So we could really just plug it into Ka straight away, rearrange, solve for X, and get the pH. And that's exactly what scientists decided to do. They said in these buffer problems, my K values are always very small, X is very small, and so I can assume that these initial numbers here basically don't change. Whatever I have in my initial row, I can just directly plug into my Ka. But then someone decided they wanted to be even lazier. Rather than solving for X from here, and then having to negative log it to get to the pH, why not just rearrange this expression so it directly gives me the pH? And this is what we call the Henderson-Hasselbalch equation. So if we take this expression for Ka, we can rearrange it. So basically people took the log of both sides and then did some clever rearrangement to get this equation right here. So these equations are the same thing. This one's just rearranged. And now we see that we have a direct equation to get the pH of a buffer solution. It's given by pKa, so of course that's negative log of the Ka, plus the log of the conjugate base over the acid. This also works for buffers composed of a weak base and the conjugate acid. And very, very similar. We use this generic formula most of the time. So we see it's always pH equals pKa plus log of whatever the base is over whatever the acid part is, whether the base is the actual base or the conjugate base. Do keep in mind that this pKa always refers to the acid. So if you have a base and its conjugate, it refers to the conjugate acid. So sometimes we'll have to use that equation pKa plus pKb add up to give me 14. But instead of going through all that ice table nonsense, we're going to use the Henderson-Hasselbalch equation most of the time when we want the pH of a buffer solution. So let's look at some simple examples. Example 1. Calculate the pH of a buffer solution that is 0.250 molar in HCN and 0.170 molar in KCN. One of the most important things you want to do right away is determine what your acid and base are, because that's how we know we're going to plug it into our Henderson-Hasselbalch equation correctly. Also, Henderson-Hasselbalch is really cumbersome. I'm just going to call it the HH from now on. So we need to know who my acid and base are when we plug it into the HH. A big clue is always whether you have a Ka or a Kb. So we can see, okay, I have a Ka for this guy, so he must be my acid. So the other guy must contain my conjugate base. And if I want to see this more clearly, I can always take my acid and I can react him with water. He's an acid, so he donates, so I'll get Cn minus, and that will create H3O plus. And now I can see KCN, that must provide me with this conjugate base, the Cn minus. So again, I have my acid and I have my conjugate base. Okay, now that I have that, all I really need to do is plug it into the HH. So first of all, instead of the Ka, I need the pKa, which, good news, really easy, is just the negative log of the Ka. So the negative log of 4.9 times 10 to the negative 10. We plug that guy into my calculator and we get 9.31. So now we just use the Henderson-Hasselbalch. pH is equal to pKa, 9.31, plus the log of the base. So that's how much Cn minus I have. So that's my 0.170 over the acid. That's my HCN. So that is my 0.250. Now we just plug that guy into my calculator and we get 9.14. So easy, much easier than going through the whole ice table nonsense. Notice again, in the KCN, we ignored the K. He's a neutral ion. We just used him to get the conjugate base Cn minus into solution. We don't care about the K at all. So that's it. Let's look at this second example. Calculate the pH of a buffer solution that is 0.750 molar in CH3NH2 and 0.525 molar in CH3NH3Cl. So I always like to identify things first. If it's not obvious, I can look here and say, ooh, I've got a Kb. This must be my base, which means this guy must contain my conjugate acid. And again, I can write an equation to confirm that. I have CH3NH2 plus water. I always take my first thing and react it with the water. It's a base, so it must accept a hydrogen. So I'm going to get CH3, NH3 plus, because I'm going to move an H plus over, and that's going to leave OH minus. So if we look here, this guy must be my conjugate, must be my conjugate acid, because this guy here is my base. And we can see that CH3NH3 plus, that's my conjugate acid. The Cl, that must just be my neutral ion. Don't care about him, so I'm going to ignore him. So once again, I'm just going to Henderson-Hasselbalch this guy. Now this time I need to be careful because I'm provided with a Kb. So first I'm going to get the pKb, which is just the negative log of that 4.4 times 10 to the negative 4, which is going to give me 3.36. But I need to get the pKa, which is going to be 14 minus the pKb. 14 minus 3.36 is going to give me 10.64. Now I can just HH it. So I've got pH is equal to the pKa, 10.64, plus the log, and I always want to put the base over the acid. So my base is this guy, so that's going to be 0.750, the CH3 and H2, and the conjugate acid, that's this guy here, so that's going to be the 0.525. So I plug that into my calculator, I get 10.80. Super easy. Always with buffers, we can use the HH. Just make sure to identify who your acid and base are and correctly calculate your pKa. So if you're given a Kb, you'll need to do that one extra step to get to the pKa before you plug it into the HH.